You've seen the headlines. Harvard astronomer claims alien technology. Manhattan-sized object accelerates near the sun. Blue light, no explanation. Something from another star system just carved through our solar system at 137,000 miles per hour. And the internet wants answers. Is 3. Atlas a comet doing what comets do? Or did we just watch something else entirely? Here's what the data actually shows. If you value documented astronomical research and factual space science like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. Also, this script is researched and factual, using sources from peer-reviewed publications in the Astrophysical Journal Letters, published August 25, 2025, by Martin Cordner and the NASA Goddard Space Flight Center team. Observational data from the James Webb Space Telescope NIR SPEC campaign conducted August 6, 2025, at heliocentric distance 3.32 astronomical units. And trajectory analysis from NASA's Jet Propulsion Laboratory navigation engineer Davide Farnocchi's report, filed October 29, 2025, measuring non-gravitational acceleration components at perihelion. Now back to the information. July 1st, 2025, 5:15 in the morning, Universal Time. The Atlas Survey Telescope at Rio Hurtado, Chile, picks up something moving. Not just moving, screaming across the star field at 0.49 degrees per day. Within hours, the Zwicky Transient Facility pulls archival images from June 14th through June 29th. The object's already been photographed, just never recognized. Observatory code W68 files. The Discovery Report to the Minor Planet Center. 122 observations from 31 different observatories flood in within 24 hours. The designation comes down fast. 3I Atlas, third interstellar object ever confirmed. The math doesn't lie. Orbital eccentricity 6.14. Not 1.01, not 1.2, 6.14. That number means the object isn't bound to our sun. It came from outside, and it's leaving. Inclination 175 degrees, almost perfectly retrograde, moving backward against the flow of our solar system's traffic. Perihelion 1.36 astronomical units from the sun, just inside Mars orbit. Hyperbolic velocity 61 kilometers per second relative to the local standard of rest. You can trace this trajectory backward through time. And it never loops around our sun. It came from somewhere else in the Milky Way. Compare that to the only other interstellar visitors. One-Eye Oumuamua, discovered October 19th, 2017, by Pan-STARRS in Hawaii. Eccentricity 1.199. Cigar-shaped, tumbling, no visible coma, no tail, dry rock moving at 26 kilometers per second. 2. Borisov, discovered August 30th, 2019 by Gennady Borisov using his custom-built 0.65 meter telescope in Crimea. Eccentricity 3.356. Classic comet with a coma and tail. Carbon monoxide rich. Gosh, looked like a normal Oort cloud visitor except for where it came from. Now 3I Atlas. Eccentricity 6.14. Twice. Borisov's escape velocity, the fastest interstellar object ever recorded. July 2nd, 2025. David Jewett and Jane Liu aimed the Nordic optical telescope at the new arrival. Clearly active, diffuse appearance. Miguel Alarcon's team at the Instituto de Astrofísica de Canarias uses the 2-meter twin telescope at Teide Observatory. Same result. Cometary activity confirmed. The Deep Random Survey in Chile, the Lowell Discovery Telescope in Arizona, the Canada-France Hawaii Telescope at Mauna Kea. All three report a marginal coma with potential tail elongation. Not an asteroid, not a dead rock. Active outgassing, dust production, the signature physics of a comet responding to solar heating. The coma diameter, measured by pre-discovery observations from the Vera C. Rubin Observatory during science validation, runs June 21st through July 3rd, 13,040 kilometers on June 21st, 18,760 kilometers on July 2nd. Growing as it approached the sun, the transiting exoplanet survey satellite had already photographed it between May 7th and June 3rd when it was 6.4 astronomical units out, active even at that distance where water ice stays frozen. Something else was driving the outgassing that far out, something more volatile than water. July 21st, 2025. The Hubble Space Telescope locks on when 3I Atlas is 277 million miles from Earth. The wide field camera captures the sharpest image yet. Teardrop-shaped cocoon of dust streaming off the nucleus, elongated toward the sun, no tail in the opposite direction. The sun-facing glow too bright to be driven by dust particles the size of visible light wavelengths. Solar radiation pressure would have blown that dust backward into a typical tail within a day. The nucleus itself invisible, buried under the glare of the coma. But Hubble's data puts boundaries on size. Upper limit on diameter 3.5 miles, 5.6 kilometers. Lower limit 1,044 feet, 440 meters. Somewhere in that range sits the solid, icy heart of this interstellar traveler. Dust loss rate from the Hubble observation, 12 to 120 kilograms per second. Consistent with long-period comets first detected around 300 million miles from the Sun. Normal cometary behavior. Material ejected from the Sun warm side, creating that fuzzy halo called the coma. Small dust grains with 1 micrometer radii blasting away at 22 meters per second. Large dust grains 100 micrometers across crawling out at 2 meters per second. The bigger the grain, the harder to push. Physics working exactly as expected for a body made of ice and rock heating up under solar radiation. The coma's color, reddish. The same tone you see in D-type asteroids, solar system comets, 2I Borisov, organic compounds called tholins. Complex carbon molecules irradiated over billions of years in interstellar space, turning the surface red, not a technological signature. A chemical signature of ancient ice exposed to cosmic radiation for eons before entering our neighborhood. August 6th, 2025. The James Webb Space Telescope turns its near-infrared spectrograph instrument toward 3I Atlas. Heliocentric distance 3.32 astronomical units. 640 seconds total exposure, split across 4 dither positions. The IFU field of view captures spectral images spanning 0.6 to 5.3 micrometers. Every molecule has a fingerprinted infrared light. Webb sees them all. Carbon dioxide dominates the spectrum, not just present, dominant. The coma CO 2 to water mixing ratio measured at 7.6 plus or minus 0.3. Among the highest ever observed in any comet, 4.5 sigma above the trend line for long period and Jupiter family comets as a function of heliocentric distance. Only one other comet comes close, C 2016 R2. A known outlier. 3I Atlas isn't just high in carbon dioxide, it's extreme. Water vapor detected at 2.7 micrometers, carbon monoxide at 4.7 micrometers, carbonyl sulfide tentatively identified. Water ice absorption bands visible in the scattered light continuum. Dust grains carrying solid water ice along with the gases. The spectral maps show enhanced outgassing in the sunward direction, exactly where solar heating hits hardest. Molecular line emission isolated by subtracting polynomial fits to the adjacent continuum. The distributions, particularly for CO2 and CO, appear relatively asymmetric, pushed by solar radiation and the comet's motion through space. The CO 2 to H2O ratio of 8 to 1 screams formation environment. Comets in our solar system typically show lower ratios. Water usually wins, but 3I Atlas forms somewhere cold, really cold. Beyond the carbon dioxide ice line and whatever protoplanetary disk it condensed from Einstein billions of years ago, orbiting a star we'll never identify. Or, second possibility, its surface spent so long exposed to galactic cosmic rays during its interstellar journey that radiation processing stripped away the more volatile ices, concentrating CO2 in the outer layers, while pristine material deeper inside never sees sunlight. A paper published November 2nd, 2025 in Astrobiology by researchers analyzing the JWST and SphereX data lays it out. Galactic cosmic ray processing. The comet's outer 15 to 20 meters eroded by high-energy particles over billions of years of drifting through the galaxy. Spectral observations reveal CO2 to H2O ratio 7.6 plus or minus 0.3, CO to H2O ratio 1.65 plus or minus 0.09 TIAS. Red spectral slopes, all consistent with a nucleus whose surface has been cooked by radiation, not by a star, but by the background roar of cosmic rays filling interstellar space. Current outgassing samples, only the processed zone. The interior material, if it's still there, stays locked away unless something cracks the nucleus open. SphereX observations reported August 24th, 2025, by the NASA team show a massive carbon dioxide gas cloud extending at least 348,000 kilometers from the nucleus. Almost a quarter of the distance from Earth to the Moon. That's not a thin wisp. That's an enormous exhalation of frozen gas turning to vapor as 3I Atlas warms up. The brightness detected at 1 micrometer wavelength. If you assume it's all nucleus, suggests a diameter of 46 kilometers for a typical 4% albedo. but 99% of that brightness could be icy fragments scattered around the nucleus. Knock the contribution down by that factor, and you're back to 5 kilometers diameter, still 10 times the estimated size of 2 I Borisov's nucleus. Zwicky Transient Facility. Data analyzed in September 2025 shows something interesting. Between May 15th and the beginning of June, the effective reflecting area of 3I Atlas held steady, a plateau, no growth. Then starting June 1st, steady brightening relative to a solid object of fixed size. The plateau phase suggests the bare nucleus before substantial mass loss kicked in. If the assumed 5.6 kilometer diameter model is off by the square root of the enhancement factor during the plateau, 5 to 10 times too bright, the actual nucleus diameter could be 15 kilometers. 20 times bigger than 2 I Borisov, mass 8,000 times greater if both objects have similar density. That raises a question. Why haven't we detected thousands of smaller interstellar objects before finding one this massive? The reservoir of rocky material in interstellar space statistically should deliver smaller visitors far more often. July 20th, 2025. Near-infrared spectroscopy from Gemini South and the NASA Infrared Telescope Facility confirms water ice absorption at 2.0 micrometers. The coma is loaded with it, not just gas. Solid grains coated in frozen water traveling with the cloud. The Neil Gehrels Swift Observatory ultraviolet observations in July and August detect hydroxyl radical emission. O molecules, the breakdown product when water vapor gets hit by solar UV light. Earth's atmosphere blocks most UV, so Swift's space-based telescope sees what ground observatories can't. The faint ultraviolet glow traces water escaping from the comet. The surprise: 3. I-Atlas releases water at a distance nearly 3 times Earth's orbit from the Sun. At that range, direct surface ice sublimation shouldn't be strong. Yet the comet spews water vapor at 40 kilograms per second, roughly the flow rate of a fire hose at full blast. The mechanism? Small ice-coated dust grains ejected from the nucleus, large surface area to volume ratio. The faint sunlight heats them efficiently, turning their icy shells to gas, extended source of water vapor, seen in only a handful of distant comets, implying a complex multi-layered structure. September 7th, 2025. The James Clerk Maxwell Telescope measures hydrogen cyanide production rate, 1.5 plus or minus 0.5 times 10 to the 25th molecules per second. HCN, one of the key volatiles in comets, formed in cold environments, preserved in icy nuclei, released when solar heat penetrates the surface. Observations by the Very Large Telescope using the MU's integral field spectrograph detect cyanide gas and atomic nickel vapor. Nickel at concentrations similar to those in solar system comets. The finding, published October 30th, 2025, notes the nickel gas detected at nearly 4 times Earth's distance from the Sun, where temperatures are too cold for metals to normally vaporize. Yet there it is, a puzzle, but one that fits within known cometary chemistry, metals locked in dust grains, released when the grains heat up and break apart. The anti-tail. 3. I-Atlas shows a faint dust stream pointing toward the Sun, not the classic tail blown backward by solar radiation pressure. The anti-tail forms because large, heavy dust grains can't be pushed by light. The comet's own internal activity, gas jets erupting from the nucleus, shove the dust outward. Solar energy increases that activity, so the dust preferentially moves sunward. Projection effect adds to the illusion. We're looking at a curved sheet of debris, and from our angle, part of it appears to lead ahead of the nucleus. Not a thruster, not propulsion. Geometry and physics of dust grain dynamics in a gas flow. Late September, early October 2025. Researchers using the Atacama Large Millimeter Array Track 3 I-Atlas approaching perihelion. The comet's position in the sky shows deviation from a purely gravitational trajectory. October 29th, perihelion day, 1.36 astronomical units from the Sun. Davide Farnocchia at NASA's Jet Propulsion Laboratory files a report. Non-gravitational acceleration detected. 2 components in the orbital plane. Radial acceleration away from the Sun, 135 kilometers per day squared, 9 times 10 to the negative 7 astronomical units per day squared. Transverse acceleration relative to the Sun's direction, 60 kilometers per day squared, 4 times 10 to the negative 7 astronomical units per day squared. Non-gravitational acceleration. The phrase sounds exotic. It's not. Every active comet shows it. Gas and dust erupting from the surface carry momentum. Newton's third law, action-reaction. Push mass one direction, the nucleus recoils the other direction. Rocket effect. Not a rocket engine, a rocket effect. Frozen volatiles turning to gas, expanding, escaping, creating tiny thrust, the comet loses mass, and conservation of momentum shifts its trajectory. Calculable, predictable, observed in long-period comets, short-period comets. And now the third interstellar visitor. Harvard astronomer Avi Loeb calculates in his October 30th Medium post that to produce the measured acceleration, the nucleus must lose at least 10% of its mass during the month-long swing near the Sun. Ejection speed a few hundred meters per second for thermal gas molecules. Momentum conservation requires massive outgassing. Half-life for evaporation 6 months at that rate. Over a month crossing perihelion distance, around a sixth of the nucleus mass would evaporate. If the mass loss rate measured earlier by Webb, 150 kilograms per second, stayed constant without producing detectable acceleration until October, the nucleus mass must be at least 33 billion tons. 33 trillion kilograms, diameter at least 5 kilometers. That math assumes cometary evaporation drives the acceleration. Loeb notes an alternative. The non-gravitational acceleration might be a technological signature of an internal engine. But before jumping to that conclusion, look at the evidence for outgassing. October 28th, 2025. A preprint posted by researchers using stereo, SOHO, GOES 19 instruments reports rapid brightening, magnitude 9 at perihelion, visible with small telescopes or decent binoculars. The comet scaled inversely with distance from the Sun to the power of negative 7.5 plus or minus 1. Extreme brightness surge. Color photometry shows the comet turned distinctly bluer than the Sun for a natural comet. Blue is surprising. Dust should redden scattered sunlight. The surface of 3I Atlas. 20 times colder than the Sun's 5,800 degree Kelvin photosphere should also shift redder. Blue suggests something else. Ionized carbon monoxide emission can produce blue color in natural comets. The intense solar radiation at perihelion strips electrons from CO molecules, creating ions that emit blue light. Alternative explanation, a hot engine or artificial light source. But absent any other evidence of technology, ionized gas fits the observations without invoking spacecraft. The blue color is anomaly number 9 on Loeb's list of unusual properties. It sits alongside the high CO2 ratio, the nickel vapor at large heliocentric distance, the anti-tail, the rapid brightening, the non-gravitational acceleration, the large inferred mass, the trajectory nearly aligned with the planetary orbital plane, and the lack of a classic dust tail in early Hubble images. 9 anomalies. Or 9 features of an interstellar comet with a formation and irradiation history unlike anything in our solar system. ESA's Mars orbiters, ExoMars, Trace Gas Orbiter, and Mars Express photographed 3. IATLAS between October 1st and 7th as it passed within 30 million kilometers of the red planet. The Cassis camera on TGO captured time-lapse sequences showing the fuzzy white dot moving against the star field. Coma visible, spanning a few thousand kilometers. Nucleus unresolved at that distance. Imaging a kilometer-wide object from 30 million kilometers away is like trying to see a mobile phone on the moon from Earth. But the coma structure, the dust distribution, the brightness profile, all consistent with an active comet responding to solar heating. November 2nd, 2025. ESA's JUICE spacecraft scheduled to observe 3I Atlas from its position farther from the object than the Mars orbiters were, but catching it just after perihelion when activity peaks. JUICE's cameras, spectrometers, and particle sensor will sample the gas and dust environment. Data won't arrive until February 2026 due to transmission schedules, but the observations happen. More data, more spectroscopy. More constraints on composition and activity. December 19th, 2025, 3I Atlas reaches closest approach to Earth, 1.8 astronomical units, 269 million kilometers, 167 million miles, still far, no threat. But ground-based telescopes, Hubble, Webb, hundreds of observatories worldwide will point at it. If Loeb's prediction holds, massive gas cloud from 10% mass loss, December's observations should reveal an enormous coma, visible hydrogen and oxygen emission, clear signs of catastrophic outgassing. If the cloud doesn't appear, if the brightness drops, if the spectrum shows no major change, then cometary evaporation might not fully explain the October acceleration. Until then, the hypothesis stands. Outgassing drives non-gravitational acceleration. Comets do this. The trajectory analysis published July 9, 2025 by Shokruz Kakarov and Avi Loeb in a paper submitted to Astronomy and Astrophysics integrates the orbits of all 3 interstellar objects backward through Milky Way gravitational potential. 3I Atlas shows larger vertical excursion from the galactic midplane than 1I Oumuamua or 2I Borisov. Thick disk origin, older stellar population, median age 4.6 billion years, roughly as old as our solar system. Possibly older. 1I Oumuamua, by contrast, traces back to the thin disk, age around 1 billion years. 2I Borisov, intermediate, 1.7 billion years. 3 visitors, 3 different ages, 3 different formation environments. Each tells a different story about planetary system evolution across galactic history. If 3I Atlas is 4.6 billion years old, it spent that entire time drifting through interstellar space after being ejected from its birth system. Gravitational scattering by giant planets during planetary migration. The same process that built our Oort cloud, hurling trillions of icy bodies into distant orbits. Some of those bodies gain enough velocity to escape entirely. They become interstellar wanderers. Every star system with planets probably does this. Eject some fraction of planetesimals during the chaotic early phase. Those objects drift. Occasionally one passes close to another star. We just happen to be that other star for 3I Atlas. The alignment of the trajectory with our solar system's planetary plane. Part in 500 chance for a random interstellar approach angle. Loeb cites this as suspicious. But selection bias matters. Atlas telescopes scan specific regions of sky. Objects moving near the ecliptic plane where planets orbit get more observation time, higher detection probability. The survey that found 3I Atlas is optimized for near-Earth asteroid detection. Those objects move near the ecliptic. Same search patterns, same sky coverage, same bias toward finding things in that plane. A truly random interstellar approach could come from any angle, but we're more likely to find the ones that happen to align with where we're looking. Loeb's argument for a technological object rests on rarity. We should have detected thousands of small interstellar objects before finding one as massive as 3I Atlas. The reservoir of heavy elements per unit volume in interstellar space doesn't support frequent delivery of giant rocks. Statistically, small visitors should vastly outnumber large ones. Yet we've seen 3 objects. 1 small, dry, tumbling rock, 1 normal-sized comet, 1 potentially very large comet, sample size 3. Drawing conclusions from 3 data points about the underlying population distribution is premature. The Vera Rubin Observatory started science observations in 2025 and immediately found 2,104 new asteroids in 10 hours. Detection rates are about to explode. In 5 years, we'll have dozens of interstellar object detections, maybe hundreds. Then we'll know if 3I Atlas is genuinely anomalous or just the first large one we happened to catch. The interstellar object number density implied by 3I Atlas discovery, 10 to the negative third per cubic astronomical unit for objects with radii greater than or equal to its size. That density estimate feeds into models of planetary system formation efficiency, ejection rates, galactic stirring processes, higher density than previously estimated from Oumuamua and Borisov alone. More interstellar stuff drifting through the galaxy than we thought. Not surprising. We're just now getting the instruments sensitive enough to see it. Comets are messy. Everyone is different. C. 2014. UN 271. Bernardinelli Bernstein has a nucleus 128 kilometers across. 500 quadrillion kilograms. Largest comet nucleus ever measured. Discovered in our own Oort cloud. Nobody claims it's a spacecraft despite being 15,000 times more massive than 3I Atlas. Comet Hale. BOP had a nucleus 60 kilometers across, outgassed for years, showed sodium emission nobody expected. Comet Shoemaker-Levy, 9 fragmented into 21 pieces before crashing into Jupiter. Comet Ison disintegrated at perihelion. Comet Lovejoy survived a solar graze that should have vaporized it. Comet Oumuamua, wait, that's the first interstellar visitor. Showed non-gravitational acceleration, no visible coma, tumbling rotation, extreme elongation. Nobody proved it's a comet. Nobody proved it's anything else either. 3I Atlas has a coma. It has a dust cloud. It outgasses water vapor, carbon dioxide, carbon monoxide, hydrogen cyanide, nickel vapor, organic compounds. It shows spectroscopic signatures of ices and tholins. It brightens as it approaches the sun. It responds to solar heating with increased activity. It displays non-gravitational acceleration consistent with rocket effect from mass loss. It has a red spectrum from radiation-processed organics. It formed billions of years ago in a cold environment around another star. It got kicked out of that system by gravitational interactions. It drifted through the galaxy, absorbing cosmic ray damage to its outer layers. It entered our solar system on a hyperbolic trajectory that will carry it back out into interstellar space. Every observation, every measurement, every spectral line matches the physics of a comet. The alternative hypothesis, alien spacecraft targeting our solar system, requires evidence beyond anomalous features. Show me the transmission. Show me the course correction that doesn't match outgassing thrust vectors. Show me the spectrography of refined metals or artificial polymers. Show me thermal signatures of power generation inconsistent with solar heating. Show me waste heat, electromagnetic emissions, trajectory changes with no gas plume to explain them. Show me something that ice and rock and solar radiation and gravity can't produce. 3. iAtlas hasn't shown that. If you value documented astronomical research like this, subscribe. It's the best way to support our work. We don't speculate. We track the data. 3 iAtlas is a comet. Here's why that matters more than the alien hypothesis. Every interstellar object carries information about its birth environment. 3I Atlas formed in a protoplanetary disk around a star we can't identify, somewhere in the Milky Way, 4 to 5 billion years ago. The high carbon dioxide ratio tells us about the temperature gradient in that disk. The presence of water ice, carbon monoxide, hydrogen cyanide, tells us the disk had the same basic chemistry as the one that formed our solar system. Organic compounds, complex carbon molecules, the building blocks for life. 3. iAtlas carries them, not unique, not evidence of biology, evidence that the same chemical processes happen around other stars. Galactic cosmic ray processing revealed by the spectroscopy tells us about interstellar medium conditions, radiation flux, particle energies, exposure timescales. 15 to 20 meters of surface erosion over billions of years gives a hard number for cosmic ray penetration depth in icy bodies. That number feeds into models of how long small objects survive in interstellar space before getting sandblasted down to nothing. Older populations, thicker disk objects, suffer more exposure because they've been wandering longer. 3. iAtlas confirms the models. The dust properties, size distribution, ejection velocities, scattering properties, constrain how cometary nuclei fracture and shed material under solar heating. The anti-tail tells us about large grain dynamics. The coma expansion rate tells us about gas flow speeds. The brightness evolution tells us about sublimation rates for different ices at different heliocentric distances. All of this applies to comets in our solar system too. Study the interstellar visitor, learn about the locals. The detection rate matters for mission planning. Comet Interceptor, ESA's mission launching 2029. We'll park in space waiting for a target. A pristine long-period comet from the Oort cloud, or, if we're lucky, an interstellar object. 3. iAtlas proves interstellar objects pass through often enough that catching one is plausible. Not guaranteed, but plausible. The diversity between Oumuamua, Borisov, and Atlas shows we need to study more than one. Every visitor reveals something different. Interceptor's rapid response design lets it chase whatever comes next. The Vera Rubin Observatory will detect an average of 1 interstellar object per year, once it reaches full operational capacity. That's the projection. 12 years of survey, 12 interstellar visitors, maybe more. Build a catalog. Compare compositions, trajectories, sizes, activity patterns. Start answering statistical questions. What fraction are comets versus asteroids? What's the size distribution? How does composition vary with stellar population age? Do thick disk objects show more cosmic ray damage than thin disk objects? Are there objects with chemistry so different from solar system material that we can identify exotic formation pathways? The next decade will tell us. 3. iAtlas isn't an alien spacecraft, it's a fossil. A chunk of ice and rock that condensed from a gas cloud orbiting a star billions of years ago got flung into the void by a planet's gravity. Spent eons drifting through galactic radiation fields and happened to pass close enough to our sun that we could see it. Every atom in that nucleus remembers its origin. Every molecule preserves a record of the environment that made it. The isotope ratios, the chemical abundances, the dust grain mineralogy, the ice crystal structure, all of it encodes the conditions in a protoplanetary disk we'll never visit, around a star we'll never find. In a region of the galaxy we can only study by catching its discarded building blocks. That's the revelation. Not that aliens sent a probe, that nature makes trillions of icy bodies around every star, ejects a fraction into interstellar space, and lets them wander the galaxy carrying samples from distant worlds. We don't need to launch Voyager probes to study other star systems. The other star systems send their Voyagers to us. We just have to watch for them, photograph them, point our spectrographs at them before they leave. 3. iAtlas reached perihelion. October 29, 2025. Closest approach 1.36 astronomical units from the Sun. Temperature at the surface spiking, ices boiling, gas jets erupting, dust grains flying. The nucleus shed mass, the coma expanded. The orbit bent slightly from pure gravitational trajectory as momentum carried away in the outgassing flow. Then it started the long coast, outward, past Mars, past the orbit of Earth, into the outer solar system. March 16th, 2026. It will pass 34 million miles from Jupiter. After that, no more close planetary encounters, just the slow acceleration as the sun's gravity weakens, until 3 I Atlas crosses back over the threshold where solar escape velocity exceeds its speed. Then it's gone, back to interstellar space. Next destination unknown. Arrival time, millions of years. In December 2025, astronomers will get their last good look. Hubble will perform ultraviolet spectroscopy, measuring sulfur to oxygen ratio, tracking hydroxyl emission, monitoring activity as the comet recedes. Webb will observe again with NIR spec, capturing post-perihelion spectra to compare with the August 6th data. Ground-based telescopes will measure brightness, coma size, dust production rate. If the mass loss predicted by the non-gravitational acceleration happened, the gas cloud will be enormous. Tens of billions of tons of material, mostly carbon dioxide and water vapor, expanding around the nucleus. Visible, measurable, undeniable proof that 3 I Atlas is outgassing like a comet does. If that cloud doesn't appear, if the predicted mass loss can't be found, then the anomaly deepens. But until December, the data says comet. The chemistry says comet. The physics says comet, non-gravitational acceleration from outgassing. Carbon dioxide, rich composition from cold formation environment or cosmic ray processing. Water vapor from ice-coated dust grains. Nickel from heated dust. Blue color from ionized carbon monoxide or possibly something else. Rapid brightening from increased sublimation rate at perihelion. Large inferred mass from brightness and lack of strong acceleration earlier in the approach. Every feature has a cometary explanation. Some require unusual conditions, ancient age, extreme cosmic ray exposure, rare formation chemistry. None require technology. The final piece of evidence lands when somebody measures the nucleus directly, not inferred from brightness, not estimated from outgassing rates. Direct imaging, Mars reconnaissance. Orbiter's high-rise camera has half-meter aperture. Resolution at 30 million kilometers, 30 kilometers per pixel, 1 pixel dedicated to the nucleus. The coma is optically thin, transparent. Light from the nucleus passes through. Measure the total luminosity from the central pixel. Set a strict upper limit on nucleus brightness. That constrains diameter better than Hubble's data by 2 orders of magnitude. If HiRISE got that measurement on October 3rd when 3 I Atlas passed Mars, mission planners might have tried. Data might exist, not yet released publicly. The nucleus size question gets answered. 5 kilometers and 15 kilometers, under 1 kilometer. We'll know. Size determines mass. Mass determines evaporation timescale. Evaporation timescale determines whether the non-gravitational acceleration makes sense for a natural comet. If the nucleus is small and the mass loss enormous, something else is providing thrust. If the nucleus is large and the mass loss modest, outgassing explains everything. One measurement, one number. The debate ends. Until then, 3. I Atlas remains what the data shows. A comet, the third interstellar object ever detected. The fastest, the most carbon dioxide rich, possibly the oldest, definitely the most scrutinized. Hundreds of astronomers, dozens of telescopes, space agencies across 3 continents. All focused on this one frozen wanderer from another star system. Not because it's artificial, because it's natural and rare and fleeting, because it carries information we can't get any other way. Because it exists at the intersection of planetary science, stellar evolution, galactic dynamics, and cosmic ray physics. Because studying it teaches us how solar systems work, how comets survive, how the galaxy mixes its material over billions of years. 3 I Atlas launched from its parent system long before Earth existed. It drifted through the galaxy while our sun condensed from a molecular cloud. While planets accreted from the protoplanetary disk, while life emerged on Earth, while species evolved and went extinct, while continents drifted, while ice ages came and went, it traveled past stars we'll never name, through nebulae we'll never photograph, across the spiral arms of the Milky Way. It absorbed radiation from supernova explosions, from pulsars, from the galactic cosmic ray background. Its surface eroded. Its chemistry changed. Its orbit bent under the gravity of passing stars and giant molecular clouds. Then, in July 2025, purely by chance, its trajectory intersected with our solar system. We saw it. We photographed it. We pointed every instrument we have at it. For a few months, this 4 billion-year-old traveler became the most observed object in space. Then it leaves, back to the void. We don't get it back. No second chance. One opportunity to extract every bit of information while it's in range. One window to answer questions about a world we'll never visit. That's why the research matters. That's why the data matters. Not to confirm aliens, to understand comets, and through comets, to understand the galaxy. In November 2025, as 3I Atlas reappears from behind the Sun, visible again from Earth, the observations resume: spectroscopy, photometry, astrometry, tracking position, measuring velocity, watching for trajectory changes. The Lowell Observatory Discovery Telescope in Arizona captured post-perihelion images October 31st. Standard amateur telescopes in the northern hemisphere should start detecting it now. Clear sky, low eastern horizon before dawn, you might see it, a fuzzy dot moving slowly against the stars. Nothing dramatic. But if you know what you're looking at, a piece of another solar system, a survivor of interstellar space, a comet older than our world, it's worth the cold morning. Chi-Cheng Zhang, postdoctoral fellow at Lowell, posted his observation to his commentary blog November 2nd. First optical detection after perihelion. 6-inch telescope worked. You don't need a research facility. You need clear skies and patience. The comet moving northward from our perspective, away from the northeastern horizon, window of visibility in morning twilight when it's just above the horizon, but the sun is still far enough below that the sky isn't too bright. Time sensitive. Every day it moves farther from the sun, cools down, fades, activity drops. The coma shrinks. By late December it might be too faint for amateur scopes. Professional instruments will track it longer, but eventually it fades from sight. Then it's gone. Left the solar system, traveling outward at 61 kilometers per second, plus whatever boost it got from the gravitational slingshot past the sun, headed nowhere in particular. Destination, the galactic disk. Time to next stellar encounter. Unknown. Probability it ever gets detected again, 0. That's the context for 3I Atlas. Not a mystery. A visitor. Not artificial. Natural. Not permanent. Temporary. We get one shot at this. The data we collect now is all we'll ever have. The spectrum from Webb, the images from Hubble, the trajectory data from JPL, the spectroscopy from ground observatories, the ultraviolet observations from SWIFT, the photometry from hundreds of amateur astronomers. That corpus of data is the permanent record. Future researchers will mine it for decades. New analysis techniques, better models, improved understanding of cometary physics. They'll extract more information from the same observations, but the observations themselves can't be repeated. 3I Atlas won't come back. The lesson from all 3 interstellar visitors: they're diverse, Oumuamua, dry and tumbling, Borisov, classic comet with carbon monoxide, Atlas, carbon dioxide, rich with cosmic ray-processed surface. No two alike. The galaxy makes trillions of these objects, each one different. Different formation environment, different ejection mechanism, different exposure history, different trajectory. Some rocky, some icy, some pure ice, some young. Some ancient, some from thin disk star systems still forming planets, some from thick disk systems so old their planets are long stabilized. The variety reflects the variety of stars, of planet-forming disks, of ejection dynamics. Nature experiments with every possible configuration, ejects samples into the galaxy, lets them drift for billions of years. We catch the ones that happen to pass close. What we learn: planetary systems are messy, diverse, creative in ways we're still mapping out. 3, Atlas adds one more data point. High carbon dioxide, low water, lots of carbon monoxide, traces of hydrogen cyanide and carbonyl sulfide. Ancient, processed by cosmic rays, probably 5 kilometers diameter, or maybe larger, definitely larger than Borisov, possibly the oldest comet ever observed. Non-gravitational acceleration from outgassing, rapid brightening at perihelion. Blue color possibly from ionized carbon monoxide. Anti-tail from large dust grains, nickel vapor at large heliocentric distance. Everything fits a comet model if you accept unusual formation conditions and long interstellar exposure. Nothing requires technology unless you ignore the cometary explanations. The alien hypothesis requires extraordinary evidence. Anomalous features aren't extraordinary evidence. They're just features we haven't seen before. The galaxy is bigger, older, more complex than our experience. Interstellar comets come from environments we've never sampled. They undergo processes, cosmic ray irradiation over billions of years, that solar system comets don't experience. Expecting them to match solar system comet statistics perfectly is naive. They're outliers by definition. They form somewhere else. Comparing them to Oort cloud objects and declaring them anomalous when they differ is circular reasoning. Of course they differ. Different origin. That's what makes them interesting. 3I Atlas is interesting because it's a comet. Because it demonstrates that planetary systems around other stars make icy bodies with familiar chemistry, but different abundances. Because it shows what billions of years in interstellar space does to ice and rock. Because its discovery proves we can detect these visitors, track them, study them before they leave. Because it validates the models predicting interstellar object flux through the solar system. Because it gives mission planners like the Comet Interceptor team hope that targets exist within reach. Because it expands the sample size from 2 to 3, bringing us fractionally closer to statistical understanding of the interstellar population. December 19th, 2025. Mark the date. 3I Atlas. Closest approach to Earth, 167 million miles away. Far. Safe. Observable. The telescopes will be watching. The spectrographs will be recording. The data will flow in. By January, we'll know if the mass loss happened. By February juice, data arrives. By mid-2026, the analysis papers drop. Peer review, publication, citation. The permanent scientific record grows by another chapter. 3I Atlas, third interstellar object, identified and characterized. Comet, not craft. Natural, not artificial. Ancient wanderer, not alien probe. One more piece of the galaxy. Briefly visible, studied intensely, now departing back into darkness. That's the story. A comet from another star system screamed through ours at 137,000 miles per hour, outgassed carbon dioxide and water vapor at rates that bent its trajectory, brightened to magnitude 9 as it swung past the sun, turned slightly blue from ionized gases, displayed an anti-tail of heavy dust grains, showed non-gravitational acceleration consistent with rocket effect from mass loss, carried spectroscopic signatures of billions of years of cosmic ray exposure, us, and gave us 4 months to photograph and analyze it before it leaves forever. We did. We photographed it. We analyzed it. The data says comet. The chemistry says comet. The physics says comet. Everything else is speculation. If you find debris from a shipwreck washed up on a beach, you don't claim it's a submarine just because the wood is waterlogged and the metal is corroded. You recognize that seawater and time change materials. 3. Atlas is debris from another planetary system, washed up in our solar system after billions of years in the interstellar ocean. It looks different because the environment it passed through was different, but it's still ice and rock, still a comet, still obeying the same laws of physics that govern every other frozen body in the universe. No exceptions needed. No alien hypothesis required. Just chemistry, radiation, gravity, and time. And that reality, properly understood, reveals more about the galaxy than any science fiction alternative ever could.